Okay, motivated by the fact that students generally have a lot of difficulty understanding proportionality, and given the inability of students to apply any sophistication to the process of graphing. Students tend to graph by plugging numbers in and making tables and then constructing a graph, or even worse, by using a calculator to do that, and bypass the important concepts involved with graphs of functions. Now, done right and used to develop a real sophistication, both of those processes can work, but that's not the way they appear to be used in most curricula. Okay, so motivated by this, this is a graphical geometric basis for defining power functions and constructing their graphs. So immediately, here's a series of 3 graphs. Now there's some details here that I'm not going to talk about just yet, but in each case we have x values that double. Each x value is double the previous, so that this x value is twice as big as this one twice as big as this one twice as big as this one twice as big as this. We don't put any numbers on these x values. These are just, these x values could stand for any numbers as long as those numbers are doubling. And then y values. Now the y values aren't doubling, but they're changing by a constant factor. That factor is about 1.3. Each y value is about 1.3 times as big as the previous. Now I'm just estimating. I just, didn't measure this out carefully, but we could think of the factor being 1.3. So from here to here, y gets 1.3 times larger. From here to here, again, 1.3 times larger. And of course, the additional 0.3 gets bigger and bigger. And I probably did do a really good job of doing that. Again, I didn't measure it, just representing the process. So we match up our x values with our y values. Now I choose to match this x value with this y value, giving me this point. Then this x value with this y value, giving us a point here that I didn't, it's a little hard to see that point. This x value with this x value, giving us this point, this x value with this x value, and so forth. And these points aren't perfectly located. It's all done by hand. This is a hand-sketched graph approximating a certain type of a function. Okay, and down here we do the same thing. The difference is, in this case, the graph is concave up. It's increasing faster and faster. This one's increasing, but more and more slowly. This graph in this graph, the y value more than doubles when x doubles. Up here, y value less than doubled when x doubled. If the y value more than doubles when x doubles, then the graph is going to have this characteristic. Okay, so here's a y value, here's a y value, it's a little more than twice as big, another y value a little more than twice as big. And here are some doubling x values. Well, I just pair these up to get these points, and right there's my graph. Down here, my y factor is less than 1. Okay, so my y factor in this case, probably about 0.7, meaning that our first value is here, our second value is about only 70% or 7/10 of that down here. And then our next one is 70% of that, 70% of that, and not using exactly 70%, but if we did, it would come up pretty close to what we see here. And then our doubling x values, so we match our first y value with our first x value, second y value with the second x value, and so forth. And of course, if the y is decreasing every time x doubles, we're going to have a graph that starts higher than it ends. Furthermore, well, there are other characteristics to this graph. And they're important characteristics, so I'll mention them. First of all, with this graph, there's no limit to how many times we can cut x in half. There's no limit to how many times we can cut y in half. So that cutting x in half increases y. If y is decreasing, if y changes by a factor of 0.7, as we go from one x value to the next, moving to the right, then moving to the left, it's going to change by a factor of 1 over 0.7, 1 divided the reciprocal factor, which would be about 1.4. So if we go from here to here, each y value is about 1.4 times as great as the previous. Now, if we keep doing that, now remember that we can keep cutting x in half forever. Okay? If we can keep cutting x in half forever, then we can keep increasing y by a factor of 1.4 forever. If we do that, well, the y values grow, and they grow faster and faster. If we keep doing that forever, then there's no limit to how big the y values can be, and that creates what we call an asymptote with the y-axis. The graph approaches the y-axis but never gets there because, of course, no matter how many times we cut x in half, we never get to 0, which means our x-coordinate never gets to 0, which means our graph never gets to the y-axis. And again, as we said, no limit to how big y can get. So y keeps getting closer and closer, the graph keeps getting closer and closer to the x-axis as it gets higher and higher, but it never gets there, and there's no limit to how high it can go. That would be called a vertical asymptote. There's also a horizontal asymptote. As we go this way, the y values keep decreasing by a factor of 0.7. No limit to how many times we can double x. Although, as we keep doubling x, the intervals get pretty huge pretty quickly. The y keeps decreasing by a steady factor, meaning that the graph is approaching the x-axis as an asymptote, meaning that as we go further and further to the right, the y gets closer and closer to the x-axis. There's no limit to how close it can get to the x-axis, and there's no limit to how far it can go out that way. In the case of these graphs, there's no limit to how many times we can cut x in half. And since y increases when x increases, y is going to decrease when x decreases, so there's no limit to how many times we can keep reducing y by whatever the factor is here. So that x gets closer and closer to 0, and y gets closer and closer to 0. No limit to how close x can get, and there's no limit to how close y can get. So the graph is going to approach the point 0, 0, and we're going to call that a limiting point. We never actually get there, but we get as close as we might wish. If we cut x in half enough times, we can make it, we can pick any degree of proximity. Within 1/millionth of an atomic diameter, yeah, cut x in half 20 or 30 times and we'll get there. Okay? Same with y. Even if we're not cutting it in half, well, here we'd be cutting it by a little more than half. Here we'd be cutting it by a little less than half, but eventually it's going to get as close as we want to 0. It therefore makes sense that we include 0, 0 on these two graphs. Whereas on this graph, we have an asymptote at x equals 0. X equals 0 being the coordinate of the y-axis. Okay, so those limiting processes and the idea of a limiting point that we go ahead and include on our graph when that's feasible. And the opposed idea of an asymptote down here. These are very important mathematical ideas, and it's worth thinking about right now. Now, all these graphs are constructed by a single type of rule, that the y changes by a certain factor every time x doubles, whether that factor is between 1 and 2, or greater than 2, or less than 1. We can get functions of this nature. So these are three ways power functions can look. There's actually a fourth way. If y doubles when x doubles, and you can think about this, you get a straight line. Okay, and you should probably think about that. It's a good idea to think about that. Okay, well, anyhow, these are all power functions, and this process can be used to define the power functions, and we can talk about the family of power functions. All of these graphs represent functions in the same family. Now we're going to go on and look at the algebra, the algebraic representation of power functions and connect it to these graphs.